What if, instead of asking a service to do something and waiting for the answer, you put a message in a box and let the service pick it up when it's ready? That's the core idea behind message passing Dataflow, and it solves several of the problems that make synchronous RPC difficult in large systems. A message broker is a piece of infrastructure that sits between the sender and the receiver. The sender, called the producer, sends a message to the broker. The broker stores it. The receiver, called the consumer, reads from the broker when it's ready to process. Prominent examples include RabbitMQ, Apache ActiveMQ, HornetQ, NATS, and Apache Kafka. Each has different performance characteristics and delivery guarantees, but the basic model is the same. This decoupling produces 4 concrete advantages the book names. First, it acts as a buffer when the consumer is slower than the producer, or temporarily offline. Messages accumulate in the broker until the consumer is ready. In a synchronous system, a slow consumer causes the producer to block or fail. With a broker, the producer keeps moving. Second, it can redeliver messages automatically if the consumer crashes during processing. The message is re-encoded and processed again by a healthy consumer. This durability guarantee is built into the broker, not something you have to implement yourself. Third, the producer doesn't need to know the consumer's address. It publishes to a topic or a queue. Any number of consumers can subscribe. This decoupling means you can add new consumers, new analytics pipelines, new notification services, without touching the producer at all. Fourth, one message can go to multiple consumers through fanout. One event order placed can simultaneously trigger inventory updates, payment processing, and email confirmation, all independently. The trade-off, message passing, is one-directional. The producer fires and moves on. If you need a response, you need a second message in the opposite direction, which makes the programming model more complex for request-response workflows. Here's a scenario that illustrates exactly when message brokers win over synchronous RPC. An e-commerce platform processes orders. When an order is placed, 4 things need to happen: inventory must be decrement, payment must be charged, a confirmation email must be sent, and a fraud check must be run. All 4 are separate services. With synchronous RPC, the order service calls all 4 services and waits for each to respond before returning a response to the user. If any one of those services is slow, the email service is backlogged, the fraud check API is having latency spikes, the order response is delayed. If anyone fails, the order fails. The order service is tightly coupled to the availability of 4 downstream systems. With a message broker, the order service publishes one event, order placed. All 4 downstream services are subscribers. Each picks up the event independently, processes it at its own pace, and handles its own failures. If the email service is down for 10 minutes, emails are delayed by 10 minutes, but orders still complete, payments still process, inventory still updates. The order service itself doesn't know or care that the email service had a problem. The book frames this as the key architectural distinction. Synchronous RPC tightly couples the availability of the caller to the availability of every service it calls. Asynchronous messaging decouples them. Now, encoding still matters in message-based systems. Every message has to be encoded into bytes when produced and decoded when consumed. If a producer uses protocol buffer schema version 3 and a consumer uses version 2, the consumer must be able to handle fields it doesn't recognize, the same forward compatibility requirement that applies to databases in RPC. Kafka in particular has adopted Avro with the Confluence schema registry as its standard encoding strategy. Each message carries a schema ID, and the registry ensures consumers can always resolve the writer's schema. The encoding choices from earlier in this chapter show up directly in how message-based systems handle evolution. The actor model is a programming model for concurrency. Instead of threads sharing mutable state, which leads to locks, races, and deadlocks, each actor is an independent entity with its own private state. Actors communicate exclusively by sending and receiving messages. One actor's state is never directly accessible to another. That isolation is the core of the model. Erlang popularized the actor model in the 1980s. Erlang was built at Ericsson for telecommunications systems that needed to run continuously for years, process millions of concurrent connections, and survive node failures without stopping. Erlang's OTP framework established the patterns, actors, message passing, supervisors that restart failed actors, and hotcode loading that lets you deploy new code without restarting the system. Akka brings the actor model to the JVM, Scala, and Java. Akka actors process one message at a time from their mailbox, maintaining internal state between messages without needing locks. Orleans from Microsoft Research does the same for .NET, calling actors grains. Distributed actor frameworks extend the model across multiple machines. In Akka cluster, actors can run on any node in the cluster. Sending a message to a remote actor looks identical to sending a message to a local actor. The framework handles serialization, routing, and delivery. In Erlang, distribution is built into the runtime from the start. A process on one Erlang node can send a message to a process on another node with the same syntax as a local send. But distributed actors have the same encoding problem as everything else in distributed systems. When you send a message from one actor to another across a machine boundary, that message must be serialized. If the sending actor is running old code and the receiving actor is running new code, the message format must be backward compatible. This means the same rules apply, using coding formats that handle schema evolution gracefully. Akka has its own serialization infrastructure that can be configured to use protocol buffers or Avro. Erlang's built-in term format has its own versioning considerations. The through line of this entire chapter: in a distributed system, any part can evolve independently. Encoding formats are not just about efficiency. They're about maintaining correctness across the time dimension as code changes, as schemas evolve, as systems grow. Choose formats that make evolution safe by design, not by convention.